Hello, this is Professor Doug, and we are going to dive into Chapter 5 on torsion. And so we'll look at a couple of examples in Excel once again, and one of them will be on calculating torques in a rod, and the other will be a power calculation from an example in Chapter 5 from Hibbler's Mechanics of Materials. So let's take a look at the first example. And the first example is here. So you have a solid steel shaft. It has a diameter of 20 millimeters, and it's subjected to two torques as shown. So you can see there's an 800 Newton meter torque at point C. This is in the upper left diagram. And there is a 500 Newton meter torque at near point A, again in the same upper left diagram. And the problem is asking us to determine the reactions at the fixed supports A and B. So we are going to look at this in terms of an analysis using Excel with two unknowns. And so we don't know what those torques are, and we're going to solve for them. Okay, so statically indeterminate. So we can enter in the given torques, and you can see all of these diagrams shows the torques and the opposing torques or the reactionary torques are given. So remember the right-hand rule convention. So the torque at C is 800 Newton meters, and that's positive per the right-hand rule convention. The torque at D is minus 500. So that's clockwise in this case, right? So what's the torque at A and the torque at B, the reactions, which we're trying to find? We don't know. So we're going to use a non-zero starter value for each. And we like to use 1 Newton meter for both of those. We do not want to use 0. Okay? And it doesn't really matter which value you do use, but we are going to use 1 to get started. So then we need the dimensions and lengths. So the diameter of the rod of the shaft was given as 20 millimeters. So we're going to convert that to meters right here. And that's 20 over 1,000. And then the length of AD, the length of BC, and the length of CD are given in meters. So we're just going to type those in. So the total length of the shaft is the sum of all of these three. So this is all given information in the upper left frame here. Okay. So then we're going to calculate the moment around point C. So the moment around point C should be 0 because of equilibrium convention. So what we have to do is take a look at all of the torques that affect that moment, and counterclockwise is going to be positive. And it's minus TB, the torque at B, which is this here, plus the 800, which was given, minus the 500, which was given, minus TA, the torque at TA. So TB and TA are going to be negative torques. 500 is a negative torque, and 800 is a positive torque. So if you just sum those all up, they should equal 0. But they don't. They equal 298. Why do they equal 298? Because we are actually summing these four values that are highlighted. So we have minus TB, which is minus 1, plus 800. That's going to give us plus 799 rather. Then we have minus 500. Okay, so that's going to give us 299. Then we have minus TA, which here is 1, which is going to give us 298. So it should be 0, it's 298. So you refer to figure B here. You see where we're going with this if you followed some of my prior examples from previous chapters. And we also know that the angle of twist, which we'll call phi here, A relative to B, is going to be 0 for this example. And that's in radians, right? However, we show a calculation of 1288. Well, similarly, if we take each torque and multiply it by the respective length, and that comes from this equation in the box here, the angle of twist, A relative to B, is TAB LAB over JG, right? So we're going to assume that JG is a constant for the entire shaft, so that could be just 1. If it's a constant, so that would go away, and that's the easiest way to treat a constant is to just assign a value of 1 to it and keep the units, of course. And so J is the polar moment of inertia, And in this case, G is going to be the shear modulus, right? So that'll be 1 in the denominator. So it's basically just TAB, LAB. So you have different torques associated with the lengths of those torques applied as we move down the rod from B to A. So that would just be a calculation here in Excel that would give us 1288. It should be 0. And let's back up. The moment around C in the x direction should be 0. It's 298. And the reason these numbers are not 0, again, is because we have these two values of 1. And we're going to use Excel solver or what if to determine what they should be to make these values equal to 0. So there's a couple of solutions here. Iteration 1 is to use data what if analysis. So data is up in the menu and what if analysis is over here. And there should be a pop-up goal seek, and you might be able to see that. And what we're going to be doing is setting cell B31, that's this flashing highlighted cell here, that's the angle of twist, equal to 0, which we know it should be, radians, by changing cell B14. So why are we changing B14 and not, that's TB, right, and not B13? Because TA doesn't appear in this equation down here to the right of the highlighted box 1288, so we don't need it. TB does. So we're going to change B14. So we're going to set a value of 0 by changing cell B14, which is just TB. And then we hit OK. And that gives us that value, right? And then we have to go to iteration 2. Use data what if analysis to set cell B25, which is the moment, equal to 0. Now it's moved from 298 to minus 346. But don't worry about that, because we already have our angle of twist set to 0, so we're good. And we know our value for T sub B. We're going to set cell B25, which is the angle of twist, equal to 0 by changing the TA, torque A value, which is still 1. So we can go back to what if analysis goal seek, and we're going to set cell B25. So we're going to click on B25, that's this, equal to value of 0 by changing the torque A, T sub A. Click OK, and we get that. So we get minus 345. Okay, so those are the solutions to this particular problem using Excel goal seek what if analysis. We probably could have used solver in this case and not had 2 iterations and just done it in 1 step. In this second example is a power calculation. So these are some of my favorite problems because they're very practical and real-world examples. A solid steel shaft AB is used to transmit 5 horsepower from motor M to which it is attached. If the shaft rotates at omega, that's your angular velocity, 175 revolutions per minute, and the steel has an allowable shear stress, tau allowable 14.5 ksi, determine the required diameter of the shaft to the nearest eighth of an inch. So this is a design problem. You can see that omega is shown here as a clockwise rotational angular velocity, and we can go forward from there, right? So what are the given values? Well, 5 horsepower, and we're just going to keep that in there for now, 5 horsepower. Omega was given as 175 RPM, and tau allowable was given as 14.5 KSI. So we have to get everything into the same units, right? So we need 1 horsepower gets multiplied by 550 to be foot-pounds per second. And 1 rev per minute is 0.1047 radians per second. Where do we get that from? It's 2 pi divided by 60. Okay? So that's 1 RPM. And 1 horsepower is 550. And 1 KSI is 1,000 PSI. So we wanted to just show these conversion factors to show you now that we want to get power out of horsepower and get it into foot-pounds per second. So power is always in energy per unit time. Okay? So foot-pounds per second, we're going to take the 5 horsepower and we're going to multiply it by 550 to get 2750 foot-pounds per second. We're going to take the omega of 175 and multiply it by this 0.1047. That's the same as multiplying it by 2 pi and then dividing it by 60. Okay. And then we're going to take tau allowable 14.5 KSI and put it into PSI. So we're just multiplying it by 1,000. Okay. So then power we know is torque times omega. So angular velocity times torque from the theory in this chapter. So that's just simply, now that we have everything in the same units, we can just say that the torque then is power divided by omega. So it's 2750 foot-pounds per second divided by 18.33 radians per second. The radians will wash out of the equation, and we'll just get, and the seconds will cancel, so we'll just get about 150 foot-pounds, okay? Now, if we take the torque, we'll go down to this example 5.4 in the box, continued. So the polar moment of inertia, J over C, in this case, C would be a diameter. Let's see if I can, a radius, sorry folks. So is equal to pi C to the fourth over 2C. Well, C to the fourth over C is going to cancel to C to the third, right? And pi over 2 stays in the equation as a constant. That's equal to the torque over tau allowable. Well, we know the torque now because we just calculated it as power divided by omega and in the converted units. And tau allowable was given. So we're going to take our torque and divide by our tau allowable in PSI, okay? And that'll give us inch-pounds per PSI. We get this number 0.124. And then the radius of the shaft. Well, we're trying to figure out the diameter, right? So that's twice the radius. And we don't know the radius, and we don't know the diameter. So we're going to call the radius, which is C, the variable C, 1. Again, you don't want to use 0. So that means that pi over 2 times the radius cubed is going to give you just simply this value, 1.570796. So about 1.571 roughly, right? All right, now here we're going to use data analysis and goal seek because T over tau allowable we've already calculated now, and it's a constant now based on prior variables of 0.124, right? What we're going to do is we're going to set cell J25, okay, which is this cell right here, J25, which is pi over 2 times C cubed. And remember, that comes from simplifying the center or the middle term in this equation because the C over 4, C to the fourth over C cancels to C cubed, right? Times pi over 2. That's equal to T over tau allowable. So you can forget the J over C on the left side of the equal signs. T over tau allowable is 0.124. This should be 0.124. Cell J24, 25 rather. It isn't. It's 1.57, okay? So why? Well, because we didn't know the radius and we just assigned a value of 1 to it. All right, so I have an arrow leading down here. Set that cell equal to 0.124. So we're going to do that by changing the dummy value or the non-zero starter value of the radius, which we just called 1. So it's very simple now. Data, what if, goal seek, and we're going to set J25 equal to a constant 0.124 by changing the radius C. We click OK, and you can see we crunched through some iterations and we're pretty close to the solution. And that means that the shaft diameter now is going to be twice the radius. The radius here was 0.430, so twice that is 0.86. The problem asks you to round to the nearest eighth inch, so that's going to be 0.875. And if you look at that in terms of nearest eighth inch, that's going to be, I think it should be 5/8 of an inch. No, it's 3/8 of an inch. Let's check that. 3 divided by 8. It's not. So 5 divided by 8 is 7/8 of an inch. How about that? 7/8 of an inch is the answer. Okay, let's see that again. So we'll go back and say that our radius is unknown, so we're going to call it 1. And in the middle of this equation, you have pi over 2 times c to the third, right? Canceling out. So pi over 2 times c to the third should equal t over tau allowable. T over tau allowable we know is 0.124. This did not equal 0.124. So you can see if we play around with the radius and make it like 0.5, it approaches 0.124, 0. Sorry, let's go back. If we make it 0.4, it approaches 124. Now it's too low. So it's somewhere between 0.4 and 0.5, but we don't want to do any kind of trial and error here. We just simply want to use goal seek. So we want to set this box here in cell J25 equal to, using what if, goal seek, set it equal to 0.124, right? 0.124, and by changing the radius, and then click OK, and the actual radius is given to satisfy that equation and that equality, and then that means that the diameter is going to be twice that 0.43 value, 0.86, round up to 0.875, 7/8 of an inch is the solution.